Good morning. Thank you to the GPD Technical Committee for the opportunity to speak today. My presentation is on the durability of structural sealants in cold bent glazing applications. So the idea behind this research is trying to develop a more holistic method of data for use in FE applications for cold bent glazing. So just a quick operational definition, though I know most of you all are aware. Cold bent glazing is the application of taking a perfectly nice and flat curtain wall, and when in construction on the building, you actually bend it into place. So you're putting a tension load on it, a permanent load, in lieu of a hot bend application. So the picture here is actually pictures of a project that were cold bent and completed in 2007 in New York City. This is the IAC building, and it was, you can see here that they're manufacturing these nice flat curtain wall, and as they put them up on the facade, they are pinning three sides of this and then bending the corners in. So what it gives is an impression of, you know, a building kind of twisting out of the earth. Right, a very unique application. There's a couple benefits with cold bending. Building things that are flat are easier probably to tolerance. The challenge is, though, is that you're putting a stress into them. And so the question is, how much stress can I put into the components of a cold bent curtain wall assembly? So this is going to be solely focused on, you know, what is happening to the sealant. And the research that we did to try to develop a more predictive model that hopefully can be used in FE in a more holistic approach. So what's good about this project is there was a paper written about it after it was fabricated. And what this paper did is it looked at durability of the insulating glass unit, but the good thing for us is we were involved. So we have all the CAD drawings and things like that to where we can actually use this in part of our data development as part of a regression analysis to try to understand durability. If you're interested, you can purchase this paper. It's out on the ASTM website. You know, just for purposes here, the units that you were seeing here on the building were 1,500 millimeter by 300 millimeter, and the bend there in the corner was approaching 750 millimeters. So that's pretty significant. We've got pictures of a mock-up of the actual bending that occurs, so you can see, you know, quite a bit of deformation here in this flat frame. What's interesting about this is FE was actually used in the project, but it wasn't necessarily used for what's happening to the sealant. It was used for a lot of the glass stress distribution, things like that. For the glass, for the sealant, it was just a mechanical determination. How much load does it take to bend this light of glass into place? And then that load was limited to 0.07 megapascal or 1 psi, which is, you know, a typical recommendation by sealant manufacturers for the allowable stress for a permanent or dead load in the project. So the purpose of our study is, you know, how do we do a more integrated methodology of design via FE analysis? How can we develop better data for people that are using FE to try to understand what type of stresses and the distribution of stress, as well as the effect of creep in the sealant that's being permanently loaded in these cold bending applications? And we did that by building physical mock-ups, focusing on the sealant behavior. We measured the deformation over time. We actually measured some of the crack propagation, so after it failed, we looked at how quickly does it fail. And then we also did FE models just to confirm that our physical, validate our physical mock-ups or make sure that there was alignment here. So our physical mock-up consisted of this assembly. So it was a, our sample was a plate, an aluminum plate with a cutout in the middle, and then we adhered another plate up underneath using a silicone sealant. And so that allowed us to, and then we had these points of attachments. We're pinning the sample here in three sides, and then we have just a simple hand jack hydraulically actuated, that can deform or bend the plate here, and then hold it in place so that we can look at what's happening with the spring-like action of the deformed plate onto the sealant, replicating what we would see in a cold bend application. And we replicated this via an FE model. So what we wanted to do is, measure what we're doing and then confirm, are we getting the same thing in our theoretical model using FE. No surprises here. Aluminum and glass are modulus around 70 gigapascal. We used a Mooney-Rivlin 2 parameter for the sealant that was used, which was a 2-part sealant. The dimensions of the plate in this instance were 500 millimeters square, and then the cutout was around 233, and our bite was 26 millimeter by 9.35 millimeters. So the first test that we did is we just started deforming the plate, and we wanted to see at what point are we going to get kind of spontaneous failure. And what we found is after X amount of extension, we saw a crack here initiate. And so what's interesting is that in the FE analysis, where this crack initiates is actually where we found the highest peak max principal stress. So kind of first off the bat, we kind of come up with, we've got a good correlation here that maybe something in our FE model is a good predictor of durability. And it can be used to perhaps help estimate failure or potential for failures in these types of applications. So we did a second test, right? We didn't want to take it to failure immediately. So what we did is we backed off the amount of deformation that we had. So we said, okay, if at 123% max principal strain in the model is going to be an immediate failure, let's back it off 20% and shoot for around 100% max principal strain. And then what we're going to do is we are going to not only measure the deformation immediately after that in the sealant after we put the stress on it, but we're going to measure what happens to the sealant as that bent plate is trying to pull it away from itself and go back to its origin to try to understand if there's a function for creep or rupture. So at a measurement of around 104.6% of peak strain, what we found is that over time you're seeing that the sealant is beginning to relax or creep or move, trying to get back to origin. So at around 210 hours, it's moved close to an inch. So at 104% max principal strain, we found that the unit failed at around 70 days. So rupture didn't occur immediately. It took 70 days for the rupture to occur, and interestingly enough, it was right in the same area where we predicted the highest max principal strain. We kept measuring, though, because we wanted to understand, okay, if we have a failure, what's it going to look like? Is it just going to spring off the building, or is it going to be slow? And what we found is over 100 days, it's actually relatively a slow process. So the idea is if you actually bend something, it's not going to be a spontaneous breakage. It's going to be probably something very visual and something that's not going to be an immediate hazard, but something that would have to be addressed if it were put under that significant of a strain. So round 3, okay, we've got one data point. If we have 2, we can draw a line and we can make all sorts of assumptions. So let's put up the, let's increase the max principal strain a little bit in between where we were at and where we know the failure point is immediately. And let's get a couple more data points to see if we can do a regression analysis. So this was, the max principal strain was at around 118%. If you ask why, it's kind of an odd number because we're using the hand jack. It's a very coarse adjustment, and we were trying to hit where we could lock it in and keep it in place and not let the, jack relax after we set it. Okay, so failure at 21 hours. So like I said, we have 2 data points now. We can draw a line and we can make all sorts of assumptions. The really good thing is if we can get 3 data points and hopefully have more of a curve or try to understand if there's a logarithmic relationship to it. And so what we did is we made an assumption with this IAC building, which has been in service for 13 or 14 years. We know the amount of displacement. We have the CAD models. We can do the FE analysis and understand what the peak principal strain was in it, and then just make the assumption that somehow it's failed. So reality, the project's not failed. There's no indication that the sealant's failing, but it gives us another point to put on our graph to see if we can start to predict at what point, or are there better ways to design cold vent glazing and incorporate this max principal strain in there to ensure or increase durability. And for this project, the max principal strain was around 20% in the model. So in putting this in a graph, what we found is that there seems to be a pretty good relationship here, obviously linear, but more than likely as time goes on, that if you start to limit the max principal strain in your designs, you're going to start to get predictable. So if this is at 20%, this is at 15%, you're starting to get into the 30 to 40 year time period of durability. And obviously, it's probably more than that, right? Because this hasn't really failed yet. But at least it's a place to start to try to develop a more robust methodology and incorporate the idea of creep or rupture or stress relaxation in these permanently loaded in permanently loaded designs. So there's some caveats to this, though, in that you have to have the ability to in your model have mesh sensitivity. If you're going to be using something as peak strain, you have to ensure that you have fine enough mesh that you're not incorporating a collection of errors in it, and that you have enough discretion in your model to accurately predict that. Because if you have too coarse of a mesh, what you'll find is that your peak strain could be very under-predicted in very coarse mesh compared to very fine mesh. So the number of elements matter. So it's not probably something that you can use in a spring type of application for modeling. So it would be involved with things like Abacus and ANSYS for more sophisticated modeling. Going back to the original project, the IAC, what they said is, okay, we can estimate the average pressure in a structural joint due to bending, and that's a good course direction for design. I think that still applies. And so what we're doing is we're just trying to find out how much force does it take to bend this glass, and then averaging that force over the area of deformation. But in concert with that, we want to do an FE model and find out what is the resulting peak strain, and then going back to our regression analysis to see if it's going to be a concern for durability on where that peak strain may last. So, I think what this concluded is that, we now have a little bit more of a robust design process and able to incorporate FE up in the front end of it versus kind of a post-production to see maybe what the stress distribution is for the cold bending using a mechanical method. In the paper we say keep strains at or below 15%. The IAC building's at 20, so maybe over time as we gather more data in the performance of that, it'll get to 20. But at least it's a start, right? I mean, it's a good, perhaps a better predictor than what we've had in the past. That's the end of the presentation.